Hello geeks, this is me Ayub from a bonus video about distributed systems. In this video, I try to provide a concise overview about distributed systems and distributed computing as an extra video lesson to the architectural patterns series. So without further ado, let's dive into the topic. First, let's explain and clarify what a distributed system is and what it's not. But before that, let me tell you something that you may not be aware of. Nearly all the software we use today is to an extent distributed or involve distributed computing. How? You're gonna know the answer in a bit. For now, let me just give you some examples. Distributed systems or distributed computing is all around us. Google search engine, Amazon platforms, Netflix, blockchain, online gaming, money transfer and online banking, and the list goes on. Probably the most straightforward and the simplest example of distributed systems is the client-server model, which I assume you are familiar with, and if not, you can check my short video about it. I'll go back to this model for the sake of demonstration later. For now, let's go back to the fundamental question and see what exactly a distributed system is. A distributed system is a collection of separate and independent software or hardware components called nodes that are linked together by means of a network and work together coherently by coordinating and communicating through message passing or events to fulfill one end goal. Nodes of the system could be unstructured or highly structured depending on the system requirements. In any case, the complexities of the system remain hidden to the end user, be it a human being or a computer, and the whole system appear as a single computer to its users. Alright, let me repeat with the written words now. A distributed system is a collection of separate and independent software or hardware components called nodes that are networked and work together coherently by coordinating and communicating through message passing or events to fulfill one end goal. Nodes could be unstructured or highly structured depending on the system requirements, and the complexities of the system are hidden to the end user, making the whole system appear as a single computer to its users. So basically, it's just a bunch of independent computers that cooperate to solve a problem together. I know it sounds simple, but it's a hell of a world under the hood. Before we continue though, I just want to say that two programs communicating with each other on the same computer is not necessarily a distributed system, even though they work together to achieve the same goal. A client-server model that uses the same computer is not a distributed system. This is important to know. Of course, there is the exception of parallel multiprocessor computers, but for the sake of simplicity and clarity, let's not tackle complicated examples. That's because for a system to be called distributed as opposed to centralized or parallel, the following conditions needs to be true. First, no shared clock. Computers have clocks, also called timers, which are critical electronic devices that keep track of oscillations, and they help the computer to have its own notion of time. This in turn helps to determine the order between events and regulates the time and speed of the computer operations. If two programs communicate using the same computer, they basically have the same clock. This leads us to another requirement for distributed systems, which is that each element in this system has to have its own processor, and harmony is achieved through coordination and synchronization. The second principle is no shared memory. This is another key feature of distributed systems. This means nearly each process has its own independent memory to work with, and state is distributed throughout the system. Concurrency is another important characteristic of distributed systems, which means that software and the hardware components of the system, also called processes, are autonomous and execute tasks concurrently. And last but not least, heterogeneity and loose coupling, which means the processors are independent and separate from each other and they have different speeds. Even though heterogeneity and loose coupling are not necessary, almost invariably nodes in distributed systems run different operating systems, and components can be built with different technologies and run on different platforms. Before moving on to basic concepts about distributed computing, I just want to mention a couple of notes. First, a distributed system is a dynamic system that allows computers or nodes to join and leave at will. This has many advantages, as we'll see later, but also it introduces some challenges and overheads, such as in case of open distributed systems, security issues, and the extra work of managing the organization and membership of nodes. The second thing I want to say is that nearly all existing large distributed systems, especially modern ones, are overlay networks. What in the universe is an overlay network? An overlay network is a virtual network that was possible to build thanks to an underlying network network infrastructure. Put simply, an overlay network is just a network on top of another network. For instance, peer-to-peer networks such as blockchain and BitTorrents are overlay networks. That is to say, they are networks on top of the internet. Voice over IP is another network over the internet, so it's also called an overlay network. Okay, I hope by now you have a fair idea about what a distributed system is and can tell whether a system is distributed or not. Good. Now let's talk about some important basic concepts about distributed computing. Okay, so distributed computing is a type of computing over distributed systems, right? So this means that distributed computing is more than distributed systems. It's a broader term and it is concerned with building and establishing computing models for distributed systems and working out algorithms to solve problems related to such systems. Cloud computing is a good modern example of distributed computing. Other examples of distributed computing solutions are platform as a service, infrastructure as a service, serverless, etc. Now, we will keep things simple and talk only about basic distributed computing concepts. Alright, so one of the very basic concepts that you should know about is the notion of a node. A node is a software or hardware component that has its own processor and memory and is able to communicate with the rest of the system. Nodes form open groups, that is to say, a network of nodes that is open to the external world, and thus joining the network is easy, and also external entities can communicate with the system easily. The internet is one big giant distributed system that falls under this category. Nodes can also form closed groups, which are restricted in terms of membership, authentication, and resource accessibility. Intranets are an example of that. Of course, nodes can communicate via messaging mechanisms such as RPC calls, REST services, etc. Another important notion is what is referred to as a resource. A resource is an asset in the distributed system that could be accessed remotely by nodes in the network or users of the distributed applications that run over the distributed system. Resources can be virtually anything, such as files, services, storage facilities, other networks, etc. Basically, a resource is anything that a node can take advantage of or use. Distribution transparency is another important concept, which denotes that everything that happens under the hood should stay invisible to the end users of the system. In other words, the dispersion of resources, the failure of nodes and failovers, migration and replication operations, etc., all should be invisible to users of the system. The way to achieve this is through an important component called the middleware. And speaking of which, a middleware in this context is a distributed systems layer that connects the nodes together and make them appear as one single supercomputer. It is a logical layer on top of the whole system. Think of it as an operating system that runs over the nodes collectively. Once this layer is established, distributed applications could be built and run over it. This middleware layer manages resources, provides communication and security services, handles failures and the other complexities of distributed computing, etc. Next is concurrency. We have talked about this concept before in the characteristics. In simple words, concurrency is the fact that multiple operations and activities are executed in parallel. These activities can interact among each other to perform a particular operation. In this diagram, for example, a simple distributed program is visualized. We could see that in phase 1, task 1 and 2 are executed in parallel and there is a simple interaction between them. Phase 2 has 3 operations in parallel and 1 cooperation between 2 of them. And as we saw earlier, concurrency is an intrinsic property of distributed systems. Alright. Coordination and synchronization. These are 2 important concepts that tackle the problems of no shared clock between processes. And also they solve the problem of data corruption and inconsistency if 2 entities try to access data at the same time. Coordination ensures the smooth collaboration between operations and activities and help achieve agreement among them. Synchronization, on the other hand, orders and controls access to shared resources. The next concept is the architectural model. The architectural model dictates how the nodes in the system are organized. It defines the structure of the network as well as how nodes communicate and interact. The architectural model is extremely important in distributed computing for the sake of better management of the complexities of such systems and also for ease of maintenance. Mainly, the architecture is needed for software components, and that's because, as we said earlier, most distributed systems are overlay networks. The last concept I want to talk about is global state. Global state in distributed systems is the union of the states of the separate processes. It is sort of a global view of the system that describes its properties at a particular point in time. It's sort of the equivalent of a global object that contains all the global variables used by the software system. Now, why not use one single supercomputer that could do everything we want and save ourselves the trouble? Why use instead of that several computers and add the overhead of managing and maintaining them? That's actually a good question. And the answer is that the motives to use a distributed system instead of a single computer are many. One of the most common ones is the need for a solution where we need to reach a consensus among parties that are dispersed geographically. Examples of such cases are online banking, blockchain, bidding platforms, etc. Resource sharing is another reason why we need distributed systems such as databases or distributed file systems. Another example that falls under the same reason are peer-to-peer systems like the BitTorrent network, etc. Another case where we need a distributed system is when we cannot or it's inefficient to replicate data using one computer. Also, when scalability is of crucial importance, a distributed system is probably the optimal solution. Of course, there are other reasons why one would choose a distributed system such as availability, reliability, etc. So these are the main reasons why one would prefer to go for a distributed system. Related to the motives for using such systems are the advantages of distributed computing. But before talking about the advantages and challenges of distributed systems, let's briefly talk about their types. When talking about types of distributed systems or any kind of systems, it's important to understand that classification depends on the context and on the level of complexity we're taking into account. Are we talking about architecture? Are we classifying the system based on the end goal? Is the context related to the topology? Is it related to how coupled the nodes are, etc.? In this section, I'm going to address two types of classification. The first is general and related to the type of coupling and scale, and the second is related to the architectural model of the whole system. When talking about distributed systems in terms of scale, there are two main types of distributed computing: cluster computing and grid computing. In cluster computing systems, the underlying infrastructure is composed of identical computers that are closely connected and the management is local and centralized. Cluster computing is used to achieve high performance and minimize downtime. Grid computing, on the other hand, is a type of systems in which heterogeneity is the norm in terms of hardware, software, and technology. Nodes are dispersed over a very large area and administration is decentralized. Such systems are used when a large repository of data is involved and a lot of computing power is required. Alright, and if we're talking about architecture styles, on the other hand, distributed systems fall under one of the following categories. First, layered architecture. In this architectural model, nodes are grouped into separate layers, each with a specific goal to achieve. An example of a simple layered distributed system is the client-server model. Next, the object-based architecture. Nodes in such systems are less structured and loosely coupled than the layered model. Communication is asynchronous and elements of the system can directly interact with other elements through direct calls. The third architectural model is the data-centered architecture. In such systems, nodes communicate through a common repository. The system is based on a data center through which primary communication happens. And the last one, which is a more common one, is the event-driven architectural model. Event-driven systems achieve their goals by means of events. Nodes communicate and perform operations through the propagation of and the reaction to events. Feel free to check my video about the event-driven architectural pattern to know more. So these are the main architectural styles for distributed systems in a nutshell. Alright, let's talk now about the pros and cons of distributed computing. As always, let's start with the advantages. The first advantage I want to talk about is reliability. A defining characteristic of distributed systems is the reliable interconnection and cooperation between nodes in the whole system. This makes it easy to share data between nodes. Another great advantage is scalability. In fact, this is one of the main reasons as to why someone or an organization would opt for a distributed system. In distributed computing, scalability is a matter of adding more nodes to the system at the corresponding layer or level, or what is referred to as horizontal scaling. Another common advantage is fault tolerance. It means the system and its services will still be operational and reliable even when parts of the system goes down. Of course, as we said before, resource sharing becomes not only possible but also easy in such systems. And last but not least, increased performance. But as all matters of life, distributed systems are not a silver bullet. And actually, talking about the downsides of distributed computing is a separate topic in itself. First, failure detection. Failure detection is almost impossible in distributed systems, especially if the system is large and evolves over time. Very elaborate measures need to be taken to mitigate risks of this issue. Redundancy is a common issue among distributed systems as well. Another challenge or problem is the difficulty to achieve consistency among nodes. And finally, performance bottlenecks is a serious issue as well. Actually, when it comes to distributed systems, the more we design for failure, any kind of failure at all levels, the less problems we will have. This leads us to the final section, issues and considerations. Of the most important pitfalls when building distributed systems is the false assumptions made by developers, such as the network is reliable and secure, or the topology of the underlying network doesn't change, or that latency is zero. This leads to a poor and fragile system that breaks easily. And actually, one of the crucial principles developers and architects abide by when designing and developing distributed systems is the design for failure principle. Under this rule, there are a lot of considerations to take into account, but generally speaking, design for failure is expecting the worst case scenario in each and every aspect when the system is operational and plan for that. Alright, this should be enough for a brief overview of distributed systems. The last thing I want to say is that unlike distributed systems, nodes in a network are explicitly visible and have to be explicitly addressed. Also, a network in itself doesn't have to have a specific end goal, and it's usually not robust and secure as a distributed system. That's the difference between a distributed system and a network. Alright, I hope you've enjoyed this video and learned something new. Don't forget to subscribe. Until the next video, stay tuned.
Every time you watch a movie online, shop online, or search for something, you are interacting with a distributed system hidden by a web page or an application. They are everywhere. All these companies are running highly scalable distributed systems in order to handle millions of users and petabytes of data, but providing you a seamless user experience as if you are interacting with a single system. Even the simplest website today hosted on a cloud is running on a distributed system, because cloud itself is a distributed system designed for companies and individual software developers. The beauty of a well-designed distributed system is that users are not even aware of it and makes it feel like you are communicating with a single system. A centralized system is the opposite of a distributed system, and analyzing a centralized system will help us appreciate the need of distributed systems. Let's say you want to create an online service to buy and sell bitcoins, for which you build a website, a sleek mobile app, and host it in your machine at home. In few months, your service gets popular, your user base grows, and now your machine can no longer handle the extra load. So you decide to upgrade your computer with new CPU, more RAM, and this is vertical scaling. But it is limited. There is limited amount of memory and computer power you can get from a single machine. So at best, you're delaying the load issue. Moreover, your computer is a single point of failure. If there is a power outage tomorrow in your area, your entire service will go down. And if your users are trying to access your service from other part of the world, most likely they will experience high latency or slowness. In contrast, a well-designed distributed system can scale to billions of users. They can scale horizontally and grow or shrink on demand, which takes care of single point of failure and latency issues. A distributed system is a system of several processes running on different computers that communicate and coordinate their actions by messaging through the network, sharing a state, or working together to achieve a common goal. Let's talk about process. When you compile a Java application, it becomes a class file. A jar file is the container of all the class files, and this gets stored into your file system, just like any audio, video, and text files. When you launch the application, the operating system creates an instance of that application in the memory. And that instance is process, which is completely isolated to any other processes running in the computer, be it the same application or instances of different applications. Processes running on the same machine can communicate with each other through the network, the file system, or the memory. But since it's the same machine, it's not a distributed system. They cannot scale beyond the capacity of single machine and are vulnerable to single point of failures. Now, if you can decouple and put each of the processes in different machines, they can scale horizontally, and if any machine goes down, others can take over and maintain availability of your application. Since everything is on different machine, network is the only way for the processes to communicate with each other. Once the communication is established, we must ensure these processes maintain a shared state and work together to achieve common goal. If processes don't know about each other, then it just becomes collection of computers, not a distributed system. So, the goal here is to design distributed systems and build the algorithms in such a way that processes can collaborate with each other. Designing distributed system is no easy task, but can be interesting. We will talk about some of the best practices, algorithms, and patterns to build distributed systems in my future video.
I want to start out by talking a little bit about whether we really need to explore parallel computing or distributed computing. The key question is sort of, do we need to have faster and faster computers or more computing power that we can throw at different problems? And I think the answer to that, and you might expect me to say this, is yeah, we do need more and more power. But let me just cite a few examples. One that comes to mind right away is the use of computing in meteorology or climate research. If you think about just sort of an ordinary weather forecast for what's the weather going to be like here in Taylor in 2 days, the way that forecasting models work is essentially taking the atmosphere over some area of land, say the state of Indiana, and splitting it up into sort of cubes that are, certain width and height and depth. And for each of those cubes, trying to track the temperature and the air pressure and the wind speed and direction and the moisture and so forth, and then using that information, trying to apply various mathematical models that try to predict what's going to happen in each of those cubes over time. In order to get a more accurate forecast, or to get a forecast that takes into consideration more days with more accuracy, one important aspect of being able to do that is to reduce the size of the cubes. You'll reduce the level of error that's going to be inherent in that process by having finer grained data over what's actually taking place, say, over the state of Indiana. When you do that, however, you've now got more cubes in which you have to carry out these calculations, which means that we need to either have more computing power, or we have to deal with the fact that we aren't going to be able to forecast at all. If the computer is too slow and it produces forecasts in a longer period of time than the actual weather evolves, what we've got basically is weather verification and not weather forecasting, and that's not especially useful. And that's just one area where large-scale computing gets put to use, and there's a ton of others. So anything in computational chemistry, computational biology, protein folding, drug design, artificial intelligence research, machine learning, any kind of predictive modeling, processing images for things like games or films or educational purposes, modeling physical systems like the airflow over a wing for aircraft design or rocket design. In short, there's just no lack for problems that need more and more computing power, and there's no foreseeable end to that process in sight. So it's worth asking the question, however, whether we need to do parallel computing in order to be able to bring more power to bear on these kinds of non-trivial problems. For decades now, we've been programming single processor machines, and the single processor machines continue to get faster and larger and more capable, or at least it appears that that's the case to the untrained eye. But what I want to take a look at is what's really happening behind the scenes in terms of the increases of performance in computing in recent years. So we're going to take a look at some of the historical background behind this process and start out kind of with an overview of various performance characteristics of different processors over the years. So this table gives us some key metrics associated with different microprocessors over the years, going back to 1971, which was the year during which Intel released the 4004. This was a processor that many of you may have never heard of, but the 4004 gave rise to the 8008 and the 8080, and the 8080's successor, the 8086, is the processor from which we get the common abbreviation for processor architecture x86. So the 4004 is the great-great-grandfather of the 8086. So back in 1971, when Intel introduced this very first integrated circuit microprocessor core, these were some of the relevant characteristics. It had a quite slow clock speed by today's standards, 108 kilohertz, right? Not megahertz or gigahertz, but kilohertz. It consisted of 2300 transistors. That's a very common metric that's used to gauge kind of the complexity of a chip. How many transistors have been laid down on the silicon surface to implement whatever functionality that chip does. And then the final column here, the feature size, basically is a measure of how small the transistors are. So 10 times 10 to the minus 6, it's 10 microns, basically. That would be the basic feature size, sort of the smallest component that the manufacturer at that point was able to etch onto the chip's surface. So that's where we started back in 1971. And if we inspect some of these metrics as we go, there's some trends that are pretty clear. First of all, in terms of processor cores, in the early going, we had just a single core processor on all of these devices. And we saw kind of an inflection point here around the turn of the century, where now we started seeing cores, multiple cores being placed on a single microprocessor. So 2 cores, 4 cores, 8 cores, and so forth. And that number has pretty much uniformly grown over the last 20 years or so. And that trend is widely expected to continue. In a similar way, if we look at the transistor count on each of these chips, we see that this number also continues to sort of grow. So we went from 2,300, we crossed the million transistor barrier with the 8486 around 1990, and we are currently into the hundreds of millions of transistors about 10 years ago. And then there's this kind of gap in the data. What's happened is that the processor manufacturers have been more tight-lipped about the number of transistors that they've been able to fit onto a chip, because that's competitive information that they'd rather not reveal. Another thing that we can see here in terms of the feature size is that we've gone from 10 times 10 to the minus 6 meters, or 10 microns, up to 14 nanometers, so a factor of 1,000 times smaller in terms of the basic size of components that we can lay down on the chips. And this is as of 2016, and in more recent years, we've seen that feature size shrink even further. So we can put more transistors on the same area of silicon, which allows us to have a more capable processor. Finally, let's take a look at the clock speed here. We can see that the clock speed started out around 100,000 ticks per second. Remember from ICS that the clock speed is basically a measure of how quickly the processor can run instructions. You could think of the clock as kind of an orchestral conductor, right? In order to keep all the musicians synchronized, the conductor provides a tempo for the music to be played at. And without that, the musicians would all go off in their own direction and you'd have chaos. In the same way, the clock on a processor is a signal that gets distributed around the entire processor chip, and it provides a way for all of the components on the chip surface to behave in a synchronized way, to collaborate together to execute instructions. So the clock speed has a lot to do with the amount of computing that can be done. The faster the clock, the more computing you can do in the same period of time. So the clock speeds came up rather dramatically by 1974. Intel was clocking the 8080 at 2 megahertz, and we could see that in around the turn of the century again, we reached the 1.5 gigahertz barrier, 1.5 times 10 to the ninth. But if you look at these numbers, what you'll see since then is that the clock speeds have gone up a little, but not by orders of magnitude, right? So here in the 2015-2016 era, we're talking about 2 or 3 gigahertz compared to just 1.5 gigahertz quite a while ago. So we haven't seen nearly the increase in clock speeds that we've had in the early going. And that has a significant impact on this question of whether or not we need to go toward parallelism or whether we can continue to expect increases in the basic clock speeds. Here's another visualization of some of these metrics. So this is the transistor count by year, and you can see that this is a logarithmic scale on the y-axis, as is the case for this and the next couple of graphs. So when we see essentially a linear increase on a logarithmic scale, that corresponds to an exponential increase in the number of transistors. And you can see here we sort of run out of gas at 2010 when the chip manufacturers stopped publishing information about this. Similarly, the feature size has continued to drop essentially at an exponential rate. to where we're getting now to the point where people are starting to wonder if we can actually make smaller and smaller transistors because the process of physically manufacturing them continues to become more and more difficult. But we're still basically following Moore's law, right? This notion that we're going to see dramatic increases in performance and dramatic decreases in size over time. Here's the rub. When we think about clock speed, so here we got 10 to the 5th up to 10 to the 9th, or 1 gigahertz here at the high end of this chart. Right around the year 2000, we saw that we got off of this exponential growth curve and it sort of flattened out. So for the last 20 years or so, we've been dealing with chips that are being clocked in the handful of gigahertz range, and the performance due to increased clock speed has not increased very much at all. The reason behind that, as you may recall from the ICS class, is something that we call the power wall. When we clock a chip at a faster and faster rate, the individual transistors, as they switch, generate some heat. So they're consuming power, and the result of their activity is that heat gets generated. And the heat has become the principal constraint to the increase in the clock speeds. The ability to carry that heat away from the chip has just become prohibitively difficult, to the point where the chip manufacturers have said, hey, we can't dissipate this heat any faster than we already can. And in order to avoid damaging the chips, we simply can't clock them any faster. So this power wall, this heat dissipation problem, has basically restricted the clock speeds in the small handful of gigahertz range. On the other hand, because we've seen feature sizes decrease and the number of transistors increase, we're still able to put more and more stuff on a chip. That's also the explanation for why the number of cores has continued to increase. So we can't clock them any faster, but we can put more functionality on a single chip surface. And the way that's been done both in CPUs and in GPUs in the last 10 or 15 years has been to increase the number of processor cores. So this chart shows the number of cores on these different processors over time. Finally, we've got a linear scale here on the y-axis, but we can see that at about the time that processor manufacturers realized that they were hitting the power wall after 2000, before 2010, they started to continue to increase the complexity of the chips, the number of transistors that they're putting down on the same piece of silicon. But in order to be able to give more processing capability at the same clock speed, the number of processors per chip increased rather dramatically. And this should kind of definitively answer for us the question of whether or not we need to be able to program parallel computers. Pretty much any chip you buy today is itself a parallel computer with anywhere between 2 and 24 and sometimes more cores on a CPU. And if you buy a GPU chip, the number of cores that are available to you is in the thousands on just a single chip. So again, the bottom line is that if we're going to write faster and faster programs, we aren't going to be aided or be able to rely on increasing clock speeds to make them go faster. We're going to have to be able to understand how to write programs that can be parallelized in order to run on these multiple core and many core processors. Let's take a look at sort of the extreme of the parallel computing world, and that's an area that's usually referred to as supercomputing. So what are we talking about when we talk about a supercomputer? Well, it's a kind of a moving target. A definition for supercomputer is, and I've said right here that it's intentionally vague, but basically a supercomputer is just what's the most powerful computer currently available on the planet. And so this, the definition of supercomputer has changed over time, but we kind of know them when we see them, right? They're the most powerful machines available. One of the important metrics that's used in determining the performance of a supercomputer is what's called a floating point operation. So you might think of this as a floating point multiplication or division. And the abbreviation for floating point operation is a FLOP. Kind of an unfortunate acronym, but there we have it. And then when we talk about flops, that we're now talking about how many of those flops we can compute per second. So flops refers to floating point operations per second. So usually we have some kind of a prefix because a single floating point operation per second isn't particularly interesting. So we now have megaflops and larger numbers of floating point operations per second. Here's a little table. So megaflop, gigaflop, teraflop, petaflop, exaflop, zettaflop, yottaflop. If we look at these in terms of their base 2 or base 10 exponents, you can see they're kind of the number of floating point operations per second. And these are the numbers that are currently being used, or the scale of numbers currently being used to talk about the performance of various supercomputers. An interesting place to go and look at this information is what's known as the top 500 list. So an organization that keeps track of basically the fastest 500 known computers around the world and keeps statistics on their various performance. So you can kind of get a sense for where is the state of the art in very large scale parallel computers by checking out the top 500 list. It's top500.org. I think this is actually linked. This slide is linked to that webpage if you download this on the course website. Here's a picture of the number of cores on various of the top 500 machines over the years. So going back to the early 1990s, the number of cores on those machines was in the range of about 100 cores. And you can see here as of 2017 or 16, whatever this last value is here at the top, that these machines are now constructed of 10 to the 7th, right? That's 10 million processor cores, or in that general vicinity. So you can see that at the extreme, the very highest performing computers on the planet are parallel machines. It's not one processor that's super, super fast. It's a very large number of processors that are themselves quite performant in order to get these kinds of crazy performance numbers. So a single machine with up to 10 million processors. Pretty amazing. I mentioned the flops metric, right? The number of floating point operations per second. So this is a chart. Again, it's a logarithmic scale on the y-axis that shows the performance of various computers over the years on a particular benchmark of floating point calculations. It's called Rmax. It's basically the fastest that this computer can compute based on some standard benchmark programs. So what we can see here as of 2016 or so, the fastest supercomputer on the list was calculating in the 10 to the 5th teraflops range. So if we go back to this little table here, we can see that a teraflop is 10 to the 12th floating point operations per second. So at 10 to the 5th teraflops, that's the same thing as 10 to the 17th flops, which would be in the hundreds of petaflops range. So 10 to the 17th floating point operations in 1 second. To bring you more up to date with the latest and greatest, this is the number 1 ranked supercomputer on that top500.org website as of November of last year. They've come out with rankings in November and June, I believe. So there'll be other rankings that should be coming out shortly. But Summit is a machine built by the Department of Energy. It lives at Oak Ridge National Laboratory in Tennessee. It uses IBM Power 9 processors and a whole boatload of NVIDIA GPUs. You can see here from the core numbers that there's 2.4 million cores in this one computer, and it achieves an Rmax of 148,000 teraflops per second. So it's extraordinarily fast. This other number here of R peak, that's kind of a theoretical maximum. It could peak out at 200 teraflops per second, but the sustained performance on that standardized benchmark is 148,000 teraflops. And you can see that the rankings as we go down the chart here are quite considerably smaller in terms of the number of teraflops per second that machine is capable of. It's also a pretty cool looking computer. Here's a photograph of the installation at Oak Ridge National Lab. You can see that this is just rack after rack after rack of Power 9 based servers chock full of NVIDIA GPU chips. So if the motivation for the course isn't sufficient already to be able to make use of a whole variety of different processor cores on any machine you can pretty much buy, even at like Best Buy or Newegg, a further motivation ought to be that when you're done with the course, you'll have a fairly good idea about how you could program a computer like this one.
Welcome to our course on parallel programming. In the following weeks, we will see some of the cutting-edge technologies for parallel programming, see how to write efficient parallel programs, and learn the basic principles and algorithms of this fast-moving and exciting field of computing. In this first lecture, we give a general introduction to parallel computing and study various forms of parallelism. We will also give a summary of what you can expect in the rest of this course. The first big question that we need to answer is, what is parallel computing? So let's define it. We will say that parallel computing is a type of computation in which many calculations execute at the same time. Parallel computing is based on the following principle. A computational problem can be divided into smaller sub-problems, which can then be solved simultaneously. Parallel computing assumes the existence of some sort of parallel hardware, which is capable of undertaking these computations simultaneously, that is, in parallel. Having said that, we will take a short glance into the history of parallel computing to better understand its origin. Despite its recent rise in popularity, parallel execution was present ever since the early days of computing, when computers were still mechanical devices. It is difficult to identify the exact conception of the first parallel computing machine, but we can agree on the following. In the 19th century, Charles Babbage invented the concept of a programmable computer, which he called analytical engine. The analytical engine was able to execute various user-written programs. For this, Babbage is credited for being a pioneer in the field of programmable computers. After Babbage presented his ideas about the analytical engine, an Italian general and mathematician, Luigi Menabrea, wrote down a description of Babbage's computer. Menabrea envisioned an extension in which independent computations occur simultaneously, at the same time. His idea was to speed up Babbage's analytical engine. Modern computers based on transistor technology appeared much later, in the 20th century. Researchers from IBM, Daniel Slotnick, John Koch, and Gene Amdahl, to mention a few, were one of the early evangelists of parallel processing. Amdahl's famous quote comes from this era. He said, "For over a decade, prophets have voiced the contention that the organization of a single computer has reached its limits and that truly significant advances can be made only by interconnection of a multiplicity of computers." Regardless of Amdahl's visionary views, at the time, parallel computing did not become mainstream, but it attained a niche with the high-performance computing community. In high-performance computing, the main area of focus are parallel algorithms for physics and biology simulations, weather forecasting, cryptography, and applications that require a lot of processing power. Performance requirements of regular users were satisfied by increasing the clock frequency of the CPU, which meant that the CPU could execute a higher number of instructions per second. At the beginning of the 21st century, it became obvious that scaling the processor frequency is no longer feasible after a certain point. The reason is that the power required for the processor starts to grow non-linearly with frequency. This is known as the power wall. So instead of increasing CPU clock frequency, processor vendors turned to providing multiple CPU cores on the same processor chip, and named these new devices multi-core processors. It is interesting to note that these three stories share a common theme. Whether the need for faster computation arose from the sluggishness of a mechanical computer, limitations of the available technology, or the physical boundaries imposed by the power wall, additional computing power was provided through parallelization. This brings us to the next big question. Why do we need parallel computing? As you will learn in this course, parallel programming is much harder than sequential programming. There are several reasons for this. First, separating one sequential computation into parallel subcomputation is a challenging mental task for the programmer, and is sometimes not even possible. Usually, this means identifying independent parts of the program and executing them at the same time. However, some problems cannot be divided as shown in this figure. The second source of difficulty is ensuring correctness. We will see that many new types of errors can arise in parallel programming, making the programmer's life harder. With these increased complexities, why then would we bother writing parallel programs at all? As shown in earlier anecdotes, the main benefit of parallelization is increased program performance. When we write a parallel program, we expect it to be faster than its sequential counterpart. Thus, speed up is the main reason why we want to write parallel programs. In fact, achieving speed up is the third source of difficulty in parallel computing. The speed up discussion brings us to the next big topic, the relationship of parallel programming to a closely related discipline called concurrent programming. In spite of their connection, parallel and concurrent programming are not the same things. There are many contrasting definitions of these programming disciplines, and people sometimes disagree on what these disciplines are. We will decide on one particular definition and stick to it. A parallel program is a program that uses the provided parallel hardware to execute a computation more quickly. As such, parallel programming is concerned mainly with efficiency. Parallel programming answers questions such as how to divide a computational problem into subproblems that can be executed in parallel, or how to make best use of underlying parallel hardware to obtain the optimal speedup. A concurrent program is a program in which multiple executions may or may not execute at the same time. Concurrent programming serves to structure programs better in order to improve modularity, responsiveness to input and output events, or understandability of the program. As such, concurrent programming is concerned with questions like when can a specific execution start, when and how can two concurrent executions exchange information, and how do computations manage access to shared resources, such as files or database handles. So parallel programming is mainly concerned with algorithmic problems, numerical computations, or big data applications. Examples of such applications include matrix multiplication, data processing, computer graphics rendering, or simulation of fluid movement. Concurrent programming is targeted at writing asynchronous applications, such as web servers, user interfaces, or databases. While parallel programming is concerned mainly with speedup, concurrent programming is concerned with convenience, better responsiveness, and maintainability. The two disciplines often overlap. Parallel programming may rely on insights from concurrent programming, and vice versa. Concurrent programming may be used to solve parallel programming problems. However, neither discipline is the superset of the other. Having more clearly established what parallel programming is, let's take a look at various forms of parallelism. It turns out that parallel computing manifests itself on various granularity levels. For example, some microprocessors have historically had a 4-bit word size. Number ranges that did not fit into the 4 bits had to be represented with multiple words. This meant that variables in the 8-bit range, such as x and y, had to be represented with 8 bits, that is 2 words. Adding these two variables together required two separate add instructions, each operating on 4-bit words. Word size subsequently increased to 8 bits, then 16 bits, and eventually 32 bits. Each time this happened, several instructions could be replaced by just a single one. This meant processing more data in the same time interval. In effect, performance was improved by parallelizing operations on the bit level, so we call this form of parallelization bit level. A decade ago, we witnessed a switch from 32-bit to 64-bit architecture in commercial processors. More recently, a similar effect was achieved through the introduction of vector instructions in Intel and ARM processors. On a more coarse-grained scale, parallelism can be achieved by executing multiple instructions at the same time. Consider the following example. Here, the processor has no reason not to compute B and C in parallel. This is because neither B or C depends on the other to be computed. This form of parallelization is thus called instruction-level parallelism. Note that the computation of D, however, can only be started after both B and C have been computed. So in summary, instruction-level parallelism executes different instructions from the same instruction stream in parallel whenever this is possible. Finally, task-level parallelism deals with parallel execution of entirely separate sequences of instructions. These instructions can execute on the same or entirely different data. Bit-level and instruction-level parallelism are exploited by the underlying parallel hardware. In other words, they are in most cases implemented inside the processor itself. This course will mainly focus on task-level parallelism, which is usually achieved through software support. This level of granularity will allow us to express general parallel algorithms. The different forms of parallelism that we just saw manifest themselves on some concrete parallel hardware. It turns out that there are many classes of parallel computers out there, and we will take a look at some of them. A multi-core processor is a processor that contains multiple processing units called cores on the same chip. Processor vendors such as Intel, AMD, ARM, Oracle, IBM, and Qualcomm produce different models of multi-core processors. A symmetric multiprocessor, or SMP, is a computer system with multiple identical processors that share memory and connect to it via bus. Here, multiple execution units are not on the same chip. An SMP itself can contain multi-core processors, as is the case in this illustration. A general-purpose graphics processing unit, GPGPU, is a form of a coprocessor originally intended for graphics processing. As a coprocessor, it does not execute all user programs by default, but can execute a program when this is explicitly requested by the host processor. Field Programmable Gate Arrays, FPGA, is another form of a coprocessor which can rewire itself for a given task. Their advantage is improved performance when optimized for a particular application. Usually, these are programmed in hardware description languages such as Verilog and VHDL. Final class of parallel computers that we will mention are computer clusters, groups of computers connected by a network that do not have a common shared memory. Sometimes computers in the cluster also have coprocessors such as GPUs, and then we call them heterogeneous clusters. In this course, we focus mainly on multi-core processors and symmetric multiprocessors, which are closely related. All our examples and code will be optimized for multicores and SMPs. However, the algorithms that we will learn about generalize and can be implemented on most forms of parallel hardware. In this lecture, we learned about some basics of parallel computing. The rest of this week will focus on simple parallel programming examples and on the performance analysis of parallel programs. The second week deals with task parallelism and some basic parallel algorithms. The third week focuses on data parallelism and data parallel computations with a preview of Scala parallel collections. Finally, the fourth week will focus on data structures which are tailored for parallel computations. In the next lecture, we will learn how parallel computations are implemented on the JVM. We will see the basic primitives used for parallelism and learn about some concrete foundations for parallel programming.